there is a strange and silent question hiding in the darkness between galaxies, waiting patiently in the ancient light that crosses the universe to reach us. If gravity is meant to pull everything inward, why does the cosmos behave as if it is gently pushed apart by something we cannot see? And if the universe began smaller, hotter, and denser, why does the present-day expansion appear not to be slowing, but speeding up in defiance of every early expectation? When astronomers measure the faint glow from distant galaxies, they see patterns that should not exist in a universe governed only by matter and gravity. If space is stretching, what exactly is doing the stretching? If everything we know about gravity is correct in our solar system and around distant stars, why does the universe on the largest scales appear to obey rules that seem to drift beyond those familiar laws? These are not imaginary puzzles. They come from real measurements, real telescopes, and real data gathered over many decades. The cosmos is not simply expanding, it is challenging us to understand why. To uncover how this mystery began, we journey back to the early years of the 20th century, at a moment when physics itself was undergoing a profound transformation. Albert Einstein had introduced general relativity, a theory that reimagined gravity as the curvature of space and time. In this new view, planets did not orbit the sun because they were pulled by an invisible force. They moved along curved paths in a geometric fabric shaped by mass and energy. The equations governing this idea were elegant and powerful, but they carried with them an uncomfortable implication. If space was filled with matter, then the universe should not remain still. It should either contract under its own weight or expand outward. The mathematics refused to support a static cosmos. Yet at that time, the belief in an eternal, unchanging universe was strong. Many astronomers assumed that the Milky Way contained the entire universe. The idea of a cosmos filled with countless galaxies, each drifting through vast space, had not yet solidified into accepted knowledge. Einstein, influenced by these prevailing assumptions, introduced an additional term into his equations. This term, which he called the cosmological constant, was meant to balance the inward pull of gravity and create a stable universe that neither expanded nor contracted. It was a finely tuned adjustment, crafted not from observational evidence, but from philosophical preference. Even with this mathematical adjustment, the true nature of the universe remained hidden behind technological limitations. Telescopes of the early 20th century lacked the sensitivity to observe very distant stars with clarity. Faint smudges of light in the night sky were debated fiercely. Were they nebulous clouds inside the Milky Way, or were they something far larger and farther away? The answer arrived when astronomer Edwin Hubble used a remarkable type of star known as a Cepheid variable to measure cosmic distances. Cepheid variables pulse in a predictable rhythm, and the period of that rhythm reveals their true brightness. By comparing a Cepheid's intrinsic brightness to how bright it appears from Earth, one can determine its distance with impressive precision. Hubble identified Cepheids in several of those faint smudges and discovered that they were far too distant to belong to the Milky Way. They were entire galaxies, each containing billions of stars. This revelation shattered the notion of a small static cosmos. The universe was larger and more dynamic than anyone had imagined. But the greater surprise came when Hubble examined the light from these galaxies. Their spectra showed that the light was shifted toward the red end of the spectrum. This redshift was a signature of motion. The galaxies were receding from us, and the farther away they were, the faster they were moving. This relationship became known as Hubble's law. It was not a theoretical construct, but an empirical discovery drawn from careful measurements. The implication was profound. Space itself was expanding, carrying galaxies along with it. Einstein's static universe could not survive this evidence. The cosmological constant that once held the universe in balance suddenly appeared unnecessary. General relativity, when allowed to speak freely without artificial modifications, naturally described a cosmos in motion. Over the following decades, astronomers refined their distance measurements. They calibrated Cepheid variable stars with greater accuracy, developed more detailed redshift surveys, and built a more complete map of the cosmos. As the picture grew clearer, one expectation remained firmly rooted in both observation and theory. A universe filled with matter should slow its expansion over time. Gravity works tirelessly, pulling galaxies together, resisting the stretching of space. Even if the universe began with immense momentum, that momentum should fade gradually as the ages pass. This idea seemed secure. It fit the mathematics of general relativity and matched the behavior of a universe dominated by matter and radiation. But something subtle lingered in the data. The expected deceleration was not easy to measure directly. It required observing extremely distant objects whose light had traveled across billions of years of cosmic history. The deeper astronomers looked, the more they realized that the cosmos was not slowing in the way they had predicted. The universe was whispering a contradiction, one that would grow louder and clearer as new instruments came online. And so, the first part of this story brings us to a question that hangs over modern cosmology like a riddle. If gravity slows expansion, why do the measurements suggest something entirely different? The path to that answer would unfold not through assumption, but through some of the most surprising observations ever made about the behavior of distant stars. The effort to understand the motion of the universe deepened through the middle of the 20th century, as astronomers sought more precise clues from distant galaxies and the faint patterns written into the light they sent us. If the cosmos was expanding, then the question became not simply how fast it was stretching, but how that rate changed through time. Did the past reveal a universe slowing exactly as gravity would demand, or was some other pattern hidden in the long reach of cosmic history? To pursue these questions, astronomers required a way to see farther than Cepheid variables could reach. These stars were reliable, but their brightness limited their usefulness to nearby galaxies. What explorers of the universe needed were beacons so bright that they could illuminate distances across billions of light years. This need would eventually lead to the study of stellar explosions, but long before that breakthrough, astronomers continued refining the cosmic distance ladder. They developed relationships between different types of stars, clusters, and galaxies, assembling a chain of distance indicators that stretched gradually outward. Each link required careful calibration, and each depended on the accuracy of the one beneath it. With this foundation, redshift surveys grew more detailed. Large telescopes mapped the distribution of galaxies in three-dimensional space, revealing filaments, clusters, and empty voids arranged in a vast cosmic web. This structure itself hinted at a universe shaped by gravity acting over billions of years, pulling matter into long strands and dense knots. Yet the underlying question of whether the expansion slowed remained unsettled. Astronomers understood that to answer it, they would need to look deeper into the past. The farther one sees into space, the farther back one peers into time. Light from distant galaxies carries a snapshot of the universe as it was when that light began its journey. Observing the most distant galaxies means observing a young universe, one still dominated by denser matter, where the slowing effect of gravity should be stronger. If expansion was indeed decelerating, then astronomers expected that distant objects would appear slightly brighter than they would in a universe expanding at a constant rate. The reason is simple. If the early expansion was faster than the later expansion, then distant galaxies would be somewhat closer than they would otherwise appear, and their light would reach us with less dimming from distance. This expectation was grounded entirely in general relativity. There was no theoretical motivation at the time to consider any other possibility. The idea that the universe might accelerate rather than decelerate did not fit naturally into the physics that astronomers had tested so successfully in the solar system and in the behavior of stars. So researchers pressed onward with quiet confidence that the universe would reveal a pattern matching their predictions. What they did not foresee was how revolutionary the next set of measurements would be. As technology advanced, astronomers learned to identify and study type Ia supernovae, the brilliant explosions of white dwarf stars that that have accreted material from a companion. These events reach an extraordinary and consistent peak brightness, making them visible across immense cosmic distances. But in these early years, Type Ia supernovae were still being understood. Their usefulness as distance indicators had not yet been fully realized. The groundwork for future discoveries was being laid, but the startling implications had not yet emerged. Meanwhile, the understanding of our own galaxy and its neighbors continued to grow. Observations from radio telescopes mapped the motion of hydrogen gas, revealing the rotation curves of galaxies and hinting at the presence of unseen mass. This unseen mass would eventually become known as dark matter, another puzzle whose influence shaped the cosmos, but whose nature remained elusive. Though this mystery was separate from the question of cosmic expansion, it illustrated the same theme. The universe often offered clues that did not fit human expectations. Throughout these developments, general relativity continued to serve as the guiding framework. It predicted the behavior of worlds near and far with remarkable accuracy. Binary stars danced in agreement with its predictions. The bending of starlight around massive bodies confirmed its geometric insights. And yet none of these successes guaranteed that the theory would describe the universe correctly on the largest scales. The cosmos is vast enough that its deepest truths may only reveal themselves through the combined whispers of distant stars and subtle distortions in ancient light. By the closing years of the 20th century, attention was turning increasingly to the need for high-precision measurements of distant supernovae. Researchers recognized that these explosive events offered a way to probe the dimmest and most remote corners of the cosmos. They could become powerful tools for reconstructing the universe's expansion history. Before these breakthroughs arrived, however, astronomers remained anchored to one key assumption: gravity must slow expansion. This idea was not a guess. It was firmly rooted in the mathematical structure of general relativity. A universe filled with matter cannot accelerate outward without some additional ingredient. And yet the stage was quietly being set for one of the most surprising discoveries in all of cosmology. The instruments were improving, the techniques were sharpening. The universe, patient and indifferent, waited for the moment when humans would finally gather enough evidence to confront a truth no one had expected. The answer to the question of whether the expansion was slowing lay hidden in the faint glow of stars, whose light had crossed billions of years of cosmic history. Soon, that glow would reveal a pattern that overturned decades of assumptions. The search for that revelation brings us closer to the turning point of this story, where the universe itself would reveal that it was not behaving in the gentle deceleration that gravity alone would produce. Something else was at work, something subtle yet immense, woven into the very structure of space and time. The turning point of this story unfolded through a convergence of careful measurements, patient observation, and the willingness of astronomers to trust the evidence even when it contradicted long-standing expectations. As the 20th century approached its final years, two international teams set out to determine the cosmic expansion rate in the most direct way then possible. Their plan was simple in concept but demanding in execution. They would gather light from some of the most distant and luminous events in the universe, the explosions of white dwarf stars known as Type Ia supernovae, and use them to trace the stretching of space across billions of years. Type Ia supernovae occur when a white dwarf star draws matter from a companion until it reaches a critical condition and ignites in a runaway thermonuclear reaction. This process produces an extraordinary burst of light that briefly rivals the brightness of an entire galaxy. Because these explosions follow a consistent pattern, astronomers discovered that their peak brightness can be standardized using the relationship between the shape of their light curve and their intrinsic luminosity. This relationship, known through careful empirical study, made Type Ia supernovae reliable beacons for measuring distance across the cosmos. Their brightness allowed them to be seen much farther than Cepheid variables, making them ideal tools for probing the universe at epochs where deceleration should have been strongest. The two teams, the Supernova Cosmology project and the High Z Supernova Search Team, worked independently, using different telescopes, different analysis techniques, and different data reduction pipelines. Their shared goal was to measure how the expansion rate of the universe changed over cosmic time. If the universe was slowing, distant supernovae should appear brighter than they would in a universe with a constant expansion rate, because the early universe would have been expanding more rapidly. Instead, as the teams collected data from supernovae whose light had traveled for billions of years, a surprising pattern emerged. These distant explosions appeared dimmer than expected. They were farther away than they should have been in a decelerating universe. The data did not align with the long-held assumption that gravity was slowing the expansion. Instead, the supernovae seemed to be receding faster than predicted, as if space itself had been accelerating outward for billions of years. Astronomers approached the result with caution. Extraordinary conclusions require extraordinary scrutiny. The teams examined every possible source of error. They checked for dust that might dim the supernovae. They studied the effects of host galaxy environments. They refined their calibration methods and cross-compared their measurements with those from nearby supernovae whose distances were well constrained. No matter how the data were tested, the same result emerged. The universe was not slowing, it was accelerating. This discovery, first published in the late 1990s, changed cosmology in a profound way. It was supported by independent teams, verified through independent analysis, and grounded firmly in observations. The conclusion was unavoidable. The expansion of the universe had begun to speed up sometime over the last several billion years. Gravity, acting alone, could not produce this behavior. Something else was influencing the large-scale dynamics of the cosmos. The implications of this finding reached far beyond the supernova measurements. If acceleration was real, then it must appear in other cosmic signals as well. Over the following years, additional evidence arrived from multiple directions. Observations of the cosmic microwave background revealed patterns in the earliest light that matched a universe where matter alone could not explain the geometry. Measurements of baryon acoustic oscillations mapped the large-scale clustering of galaxies and independently supported an accelerating cosmos. Weak gravitational lensing, which traces the bending of light by cosmic structure, provided further confirmation. All these observations, emerging from different techniques and datasets, pointed to the same conclusion. The universe was not merely expanding, it was accelerating. Such a revelation demanded a name for the unknown phenomenon driving this behavior. Astronomers called it dark energy, not because its nature was understood, but because its presence was required to explain the data. Much like dark matter, dark energy represented a placeholder for something not yet fully known. It was a signpost marking the boundaries of current knowledge. The simplest explanation was to revive Einstein's cosmological constant, but now as a genuine physical term, rather than a mathematical adjustment. In this interpretation, space possesses a small but persistent energy density that remains constant as the universe expands. This constant energy acts as a pressure that accelerates the expansion. Yet even as this idea matched the observations, it raised deep theoretical questions. Why would the universe contain such an energy? Why would its value be so small, yet non-zero? And why would it grow dominant only in the relatively recent cosmic past? These questions would open new chapters of inquiry, blending cosmology, quantum theory, and the deepest puzzles of gravitational physics. For now, the first chapter closes with a simple but profound truth. The universe has forced us to reconsider our assumptions. The expectation that gravity must slow cosmic expansion was not wrong in principle. It was simply incomplete. The cosmos revealed a story more complex and more mysterious than anyone had foreseen. Through the light of distant supernovae and the patient work of generations of astronomers, the universe delivered a message written across billions of years. Something exists that causes space to stretch faster as time unfolds. What that something is remains one of the greatest open questions in modern science, and the search for its answer will lead us deeper into the fabric of the cosmos than humanity has ever traveled. For many years after the realization that the universe was expanding, astronomers believed they understood the broad outline of cosmic history. Space had stretched from a denser past, and gravity should have gently resisted that stretching, slowing the expansion across billions of years. It seemed a simple and elegant picture, one supported by general relativity and consistent with the distribution of galaxies across the sky. Yet science often advances most powerfully when familiar ideas meet precise evidence. The true turning point came when astronomers sought a method to look far enough into the past to measure how fast the universe had once been expanding. They needed candles bright enough to shine across billions of light years and uniform enough in behavior to serve as trustworthy tools. Only then could they reconstruct the universe's expansion history with confidence. Enter the extraordinary phenomenon known as a Type Ia supernova. These explosions arise when a white dwarf star, the compact and fading remnant of a sun-like star, gathers matter from a companion until it reaches a critical threshold. At that moment, the balance of forces collapses and the star ignites in a runaway thermonuclear event. This process releases an immense burst of light, bright enough to outshine an entire galaxy for a short time. But brightness alone was not the reason these explosions would become essential to cosmology. Their deeper value came from a discovery made through careful observation. The shape of their light curve, the way their brightness rises and fades, is correlated with their true luminosity. By studying this shape, astronomers can standardize their brightness and determine their true distance. The realization that these explosions could serve as standardizable candles was revolutionary. It meant that for the first time, scientists could probe the universe on truly cosmological scales, far beyond the reach of Cepheid variables. But using them required extraordinary precision. These events are rare, unpredictable, and sometimes obscured by dust or complex galactic environments. To measure them, astronomers needed rapid detection, careful calibration, and detailed modeling. It was a challenge perfectly suited to the era when digital detectors, large telescopes, and improving computational tools were transforming astronomy. Two research collaborations took on this monumental task. One was the Supernova Cosmology project. The other was the High-Z supernova search. They worked independently, using different instruments and analysis methods, not to compete, but to ensure that any shared conclusion would be robust. Each team developed techniques to identify distant supernova while they were still rising toward their peak brightness. They used wide field cameras to scan large regions of the sky, comparing images taken weeks apart to catch the telltale emergence of a new pinprick of light. These candidates would then be confirmed with spectroscopy, which allowed astronomers to determine their redshift and ensure they were indeed Type Ia explosions. Once the supernovae were identified, the true challenge began. The teams had to measure the light curves with extraordinary accuracy. Small differences in the rate at which a supernova brightens or fades can influence the inferred distance. Dust in the host galaxy can alter the observed color of the light, causing the event to appear dimmer. Even the properties of the telescopes themselves required careful correction. Nothing could be left to assumption. Every step demanded rigorous calibration, cross-checking, and statistical analysis. Through all this careful work, the goal was simple. Determine how far away these supernovae were, compare that distance to their redshift, and trace the expansion of the universe across time. The expectation was grounded in decades of theory. Distant supernovae, whose light left them in a younger universe, should appear slightly brighter than they would if expansion had remained constant. Their slight brightness boost would come from the fact that the early universe should have been expanding more rapidly, with gravity slowing it as time passed. But when the first data arrived, the numbers did not match this expectation. The distant supernovae were dimmer than predicted. Their faintness hinted that they were farther away than they should have been in a universe that was slowing down. At first, the result was met with caution. Astronomers asked whether some unseen dust might be dimming the supernovae. They checked whether the explosions might differ subtly from those seen nearby. They examined the possibilities of selection biases, calibration errors, or redshift inaccuracies. Every reasonable alternative had to be eliminated before any extraordinary conclusion could be entertained. Yet as both teams continued gathering light curves from supernovae scattered across billions of years of cosmic distance, the pattern held steady. The events were too faint. Their distances were too large. The only explanation consistent with general relativity and the data was that the universe had been expanding faster over time, not slower. This was not a discovery made in a single night. It was the culmination of years of careful observations, cross-checks, and statistical modeling. Every assumption was tested. Every potential source of error was weighed. And still the conclusion emerged with growing clarity. The expansion of the universe was accelerating. Space itself was being stretched in a way no one had previously imagined. The shock of this realization reached across the scientific world. Decades of understanding had suggested that gravity should act as a cosmic brake, gradually easing the universe into a slower drift. Instead, the universe was behaving like a car, whose engine was being gently pressed forward, not pulled back. This meant that some form of energy or effect, unnoticed until now, was acting on the fabric of space. It was as if the cosmos had been hiding a quiet influence that revealed itself only when examined across the largest possible scales. The first hints of this revelation came from these extraordinarily distant supernovae, events that shone for only a moment in cosmic time, yet changed the entire direction of cosmology. Their light carried a message written billions of years ago, a message that forced astronomers to question the completeness of their understanding of gravity, matter, and the fundamental structure of space. The discovery was undeniable. But its explanation was far from clear. What force could push galaxies apart faster with time? What energy could remain invisible and yet dominate the fate of the cosmos? And how could such an influence fit within the framework of physics that had been tested and confirmed in so many other settings? These questions would shape the next chapter of cosmology and lead to the introduction of one of the most mysterious ideas in modern science. The faintness of the distant supernovae lingered in the minds of astronomers, like a quiet contradiction that grew heavier with every new observation. If these explosions were truly farther away than expected, then the universe was not behaving according to the long-trusted expectation of deceleration. Something was altering the expansion in a way that defied the simple influence of matter and gravity. Yet before accepting such a radical conclusion, researchers returned to the data again and again, searching for any hidden factor that might account for the unexpected dimming. One of the earliest concerns involved interstellar dust. Dust can scatter and absorb light, making distant objects appear dimmer and redder. If the supernovae shone through large amounts of dust in their host galaxies, or on their long journey through intergalactic space, their true brightness could be underestimated. To investigate this, astronomers examined the colors of the supernovae. Dust does not simply dim light, it changes the ratio of colors in predictable ways. Yet the distant supernovae did not display the signatures expected from heavy dust absorption. Their faintness was not accompanied by the color distortions dust would impose. This explanation was carefully tested and found insufficient. Another possibility centered on whether distant supernovae were truly identical to nearby ones. Perhaps the explosions in the early universe differed in some subtle way, leading to less light output. But this too was examined in detail. The spectral features of distant type Ia supernovae matched those of their local counterparts. Their light curves followed the same relationships. Their rise and fade patterns behaved with the same underlying physics. If an evolutionary effect existed, it would need to be unnaturally precise, appearing uniformly across events separated by billions of years of cosmic history. Observations did not support such a scenario. Astronomers also scrutinized the methods used to standardize the brightness of the supernova. The relationship between the light curve shape and the intrinsic luminosity had been established through numerous nearby examples. Still, the teams revisited the calibration, comparing results from different telescopes and applying alternative fitting methods. They checked for selection effects, such as the possibility that only the brightest distant supernovas were being found. They examined the redshift measurements for systematic errors. They searched for instrumental biases that might affect the data. Yet every cross-check produced the same answer. The supernovae were too faint. With each test that failed to overturn the result, the possibility of cosmic acceleration grew more convincing. The teams recognized the weight of their findings. They were not proposing a new phenomenon from speculation. They were following the evidence, and that evidence was pointing toward a universe that was not simply coasting or slowing, but speeding up. The next step was to fit the observations into the framework of general relativity. When the distances and redshifts of the supernovae were compared to cosmological models, the best fit required a universe with a component that exerted a negative pressure, an effect that counteracted the gravitational attraction of matter. This negative pressure acted as a repulsive influence on cosmic scales, causing space to expand at an accelerating rate. In the mathematics of general relativity, this effect could be produced by the cosmological constant, the same term Einstein had introduced long ago for entirely different reasons. But this time, the cosmological constant was not being used to force a static universe. Instead, it arose naturally as a possible explanation for the observed acceleration. If space contained a small uniform energy density, then as space expanded, that energy would remain constant. The more space grew, the more total energy existed. This constant energy density would push space outward at an accelerating rate. It was a simple idea mathematically, but conceptually profound. It suggested that empty space was not truly empty. It carried a subtle but powerful property. Yet even as the cosmological constant provided a clean fit to the data, it prompted deep unease within the scientific community. If the constant was real, why should it have precisely the tiny value required to influence cosmic expansion only in the last few billion years? Why had it waited so long to become dominant? And how could quantum physics, which predicted an enormous energy associated with the vacuum, be reconciled with a cosmological constant, far smaller than any known theory could justify? Still, the evidence could not be ignored. The acceleration inferred from the supernovae demanded an explanation, and the cosmological constant provided one possibility. But the teams did not claim that this was the final answer. They maintained a cautious and precise tone, emphasizing that they had discovered an effect, not a mechanism. The acceleration was real. Its cause remained unknown. As news of the discovery spread, astronomers sought independent confirmations. Other probes soon began to strengthen the case. The cosmic microwave background, which preserves a snapshot of the universe when it was only a few 100,000 years old, showed patterns in its temperature fluctuations that indicated a geometry consistent with a significant energy component beyond matter. The positions of galaxies revealed large-scale clustering patterns whose scale could only be explained if the universe contained an additional ingredient shaping its expansion. Weak gravitational lensing measurements traced the bending of light across vast cosmic distances, offering yet another line of evidence for a universe that was not behaving as a simple matter-dominated system. Together, these independent observations formed a web of consistency. Each one pointed toward the same conclusion that the supernovae had first suggested. The universe was accelerating, not because of a mistake, not because of dust or calibration errors, but because something real and measurable was influencing the expansion of space. The discovery required astronomers to look again at the assumptions they had long carried. Gravity remained attractive. Matter still shaped the structure of the cosmos. Yet something else was acting on the universe in a way that grew more important as time passed. Something that did not dilute as galaxies drifted apart. something woven into the fabric of space itself. And so the search for this hidden influence began. What force could remain invisible, yet shape the destiny of the cosmos? What energy could fill space so gently that it escaped detection until astronomers measured the faint glow of stars from billions of years ago? The answer would lead to the idea now called dark energy, a concept that would reshape cosmology and raise some of the deepest questions in modern physics. The confirmation that the universe was accelerating did not arrive in a single flash of triumph. Instead, it unfolded like a slow sunrise over the scientific world, illuminating more and more evidence as independent observations came into focus. When the results from the supernova teams were first shared, astronomers responded with a cautious mixture of intrigue and skepticism. The universe had already proven itself to be full of surprises, but acceleration was a revelation that demanded the most rigorous verification imaginable. The stakes were enormous. If true, it meant that our understanding of the cosmos was incomplete in a fundamental way. Something unknown was shaping the evolution of the universe. As researchers around the world began to analyze the findings, they did not merely re-examine the supernova data. They looked toward other cosmic signals that had never been used to test acceleration before. Among these signals, the cosmic microwave background stood out as one of the most powerful tools available. This faint glow, discovered in the 1960s, is the residual radiation left over from a time when the universe was incredibly hot and dense. Its temperature is almost uniform across the sky, yet tiny variations in that temperature encode information about the geometry and composition of the early universe. When scientists studied these patterns using increasingly sophisticated instruments, they found that the geometry of the universe appeared nearly flat. Flatness alone was not shocking, but when combined with the amount of matter known to exist, it created a puzzle. Matter did not account for the energy required to produce a flat universe. Something else had to be present to balance the cosmic energy budget. When this missing component was added in calculations, its properties matched those required to drive accelerated expansion. In this way, the cosmic microwave background offered an independent voice that echoed the story told by the supernovae. The cosmos needed a component that did not behave like matter or radiation, one that influenced expansion without clustering into galaxies or stars. Another powerful clue came from the large-scale distribution of galaxies. Over billions of years, gravity has pulled matter into a vast network of filaments and clusters, with enormous empty voids in between. The scale of these structures is not random. It is shaped by sound waves that propagated through the early universe when it was still a hot plasma of particles and light. These ancient ripples left behind a characteristic scale known as the Baryon acoustic oscillation scale. By measuring this scale in the arrangement of galaxies across the sky, astronomers gained another method to trace how the universe expanded over time. When the Baryon acoustic oscillation measurements were compared to theoretical models, they too supported the idea that the universe had transitioned from decelerating to accelerating. The distance relationships preserved in the cosmic web matched a cosmos whose expansion had begun to speed up in the last several billion years. This agreement between such different types of data was striking. The supernovae traced the expansion through light emitted from dying stars. The cosmic microwave background captured the universe as an infant. The Baryon acoustic oscillations recorded the influence of primordial sound waves, and yet all these signals pointed toward the same conclusion. Further confirmation came from weak gravitational lensing, the subtle bending of light as it passes through the web of galaxies and dark matter. By measuring how the shapes of distant galaxies are distorted by this bending, astronomers can map how matter is distributed. These maps revealed a universe where the growth of structure had slowed more than expected in a purely matter-dominated cosmos. Such behavior is consistent with the influence of an accelerating expansion, which dilutes matter more rapidly over time and suppresses the formation of new cosmic structures. Again, the evidence aligned with the supernova findings. As these independent observations converged, the case for acceleration grew almost inescapable. The universe was not simply expanding, It was expanding in a way that signaled the presence of a persistent, uniform influence permeating space itself. This influence did not clump into stars or galaxies. It did not behave like any known form of matter. It revealed itself only through its effect on the expansion of the universe. Astronomers gave this mysterious influence a name. They called it dark energy, not because it was known or understood, but because the cosmos demanded that something fill this role. Dark energy became the term for whatever caused the observed acceleration. Nothing more, nothing less. It was not a theory of its own. It was a placeholder, a recognition that the universe was telling us something fundamental about its composition. Yet naming the phenomenon did not bring clarity. Dark energy remained elusive, invisible, and unlike any known form of matter or radiation. It did not fit neatly into existing theories of particle physics. It did not arise naturally from most attempts to unify the fundamental forces. Even the simplest explanation, the cosmological constant, raised profound questions. Why should the vacuum of space contain a tiny but non-zero energy density? Why should this energy dominate only in the recent cosmic epoch? And how could quantum theory predict a vacuum energy so vastly larger than what cosmology required? These uncertainties marked the beginning of a new era. Cosmology had shifted from mapping the universe to questioning its foundations. Observers and theorists alike recognized that the acceleration discovery was not an ending, but a doorway opening onto deeper mysteries. With the confirmation of acceleration, the next step was to examine the simplest model capable of explaining the data, the framework that would come to be known as the Lambda cold dark matter model. The journey toward understanding dark energy would require a full exploration of that framework, along with the puzzles it introduced. And so the scene was set for the next chapter, where the acceleration of the universe would be placed within the broader structure of modern cosmology. The moment the universe revealed that its expansion was accelerating, cosmologists were confronted with a task both urgent and profound. They had to determine not only what the observations meant, but how to place them within the broader structure of physics. The faint glow of distant supernovae had carried a message from billions of years ago, and that message was unmistakable. Something in the cosmos was causing space to stretch faster as time passed. This strange influence could not behave like any form of matter. It could not cluster into galaxies. It could not dilute in the way dust or gas would. It acted with quiet uniformity, as if woven into every region of empty space. To make sense of this newly discovered phenomenon, scientists turned to the most successful and extensively tested model of cosmic evolution, a framework built from general relativity, observations of the cosmic microwave background, the behavior of galaxies, and the growth of large-scale structure. This model is known as the Lambda cold dark matter framework. The name reflects two central ingredients. Lambda represents the cosmological constant, a possible energy associated with the vacuum of space. Cold dark matter represents the invisible mass that shapes galaxies and clusters through its gravitational influence. Together, these elements, along with ordinary matter and radiation, form the foundation of the standard model of cosmology. Yet the road to this framework was not built on speculation. It rose from decades of observations that consistently pointed toward its structure. The cosmic microwave background provided the earliest clues. When astronomers studied its faint temperature variations, they discovered that these patterns could be explained only if the early universe contained a specific mixture of components. Some of the matter had to be ordinary baryonic matter, the kind that forms stars, planets, and people. Some had to be dark matter, a form of mass that does not emit light yet reveals itself through gravitational effects. And beyond these familiar and unfamiliar forms of matter, something else was required to bring the model into harmony with observations. That something behaved like a smooth background energy permeating all of space. At first, this energy was treated as a mathematical parameter, a term in the equations that allowed the model to fit the data. But when the supernova discoveries arrived, the nature of this parameter shifted from an abstract convenience to a physical necessity. The cosmological constant provided the simplest explanation for cosmic acceleration. If space contained a small, constant energy density, it would produce a pressure that pushed the universe outward more rapidly over time. This simple assumption allowed the Lambda cold dark matter framework to match the supernova observations, while also remaining consistent with the cosmic microwave background and the distribution of galaxies. As the evidence accumulated, scientists began to quantify the composition of the universe using measurements from satellites such as the Wilkinson Microwave Anisotropy Probe and later the Planck mission. These observations revealed that ordinary matter made up only a small fraction of the cosmic total. The atoms that build stars, nebulae, and galaxies comprised roughly 5% of the overall energy budget. Cold dark matter contributed nearly 27%, shaping the skeleton of the cosmic web, but remaining invisible to telescopes. The remaining portion, nearly 68%, was attributed to dark energy, represented in the model by the cosmological constant. These percentages were not speculative guesses. They were extracted from the way light and matter behaved across the cosmos. The acoustic peaks in the cosmic microwave background's temperature fluctuations encoded information about the densities of these components. The large-scale clustering of galaxies traced the gravitational pull of dark matter. The distances inferred from supernovae recorded the influence of dark energy on the expansion of space. Together, these signals formed a consistent picture, one that was surprising in its details, but robust in its predictions. Still, the simplicity of the cosmological constant masked a deeper mystery. What was this energy? Why did it behave so differently from matter? And why did its influence grow so noticeable only in the relatively recent past? To investigate these questions, cosmologists considered a quantity known as the equation of state parameter. This parameter expresses how the pressure of a component of the universe relates to its energy density. For ordinary matter, the pressure is negligible compared to its energy. For radiation, the pressure is significant and positive, but for an accelerating universe, the pressure must be negative. In the case of the cosmological constant, the pressure is exactly the negative of its energy density, producing an equation of state parameter equal to -1. Observations from supernovae, the cosmic microwave background, and galaxy surveys all supported a value very close to this number. Within the limits of measurement, dark energy behaved exactly as the cosmological constant predicted. This did not mean that the cosmological constant was the final answer. It meant only that the data supported the simplest possible model. Nature often hides complexity behind simple patterns, and cosmologists remained aware that the true explanation might be more intricate. The Lambda cold dark matter framework was powerful, yet it was also puzzling. It offered a coherent picture of the universe, one that described the cosmic microwave background, the distribution of galaxies, and the accelerating expansion with remarkable accuracy. But it did so using a component whose nature remained unknown and a constant whose theoretical origin defied explanation. It worked, but it raised profound questions. Why should the energy density of dark energy have the tiny value inferred from observations, when quantum field theory suggested that the vacuum energy should be unimaginably larger? Why should dark energy begin to dominate the universe only in the last few billion years, long after galaxies had formed? These puzzles were not flaws in the observations. They were reflections of how incomplete our theoretical understanding remained. And so the chapter closes with a sense of both clarity and intrigue. The universe has revealed its broad composition with remarkable precision. The Lambda cold dark matter framework provides the most successful description of cosmic evolution ever constructed. Yet its success does not bring final answers. Instead, it opens the door to some of the deepest mysteries in physics, mysteries that would lead researchers to question not only the nature of dark energy, but the very foundations of gravity itself. The more scientists explored the implications of the Lambda cold dark matter framework, the more they recognized that they were standing before an unusual crossroads. On one side of the path lay the observations themselves, clear and consistent across multiple techniques. On the other side lay the theoretical foundations of physics, which struggled to accommodate the existence of a constant energy density spread evenly through space. The cosmological constant fit the data with remarkable precision, yet its presence raised questions that touched the deepest layers of modern science. To understand these questions, one must appreciate how the cosmological constant behaves within the mathematics of general relativity. In that theory, the curvature of space and time is shaped by the distribution of energy. Matter bends space-time, radiation bends it, even light with no rest mass bends it. But the cosmological constant plays a different role. It acts as a pressure that does not change as the universe grows. It does not dilute. It does not weaken. It remains fixed in value, influencing the cosmic geometry with quiet persistence. This constant pressure drives accelerated expansion by pushing on the fabric of the universe itself. Such behavior may sound exotic, yet it arises naturally from Einstein's equations when a constant term is included. The challenge is not in the mathematics but in the physical interpretation. What could give empty space this constant energy density? Why would the universe contain such an ingredient? And why would the value be so small when compared to the enormous quantities predicted by quantum field theory? These puzzles were recognized immediately once dark energy entered the cosmological vocabulary. They did not undermine the data. Rather, they revealed how incomplete our theoretical understanding of the vacuum remained. As cosmologists explored the implications of the Lambda cold dark matter framework, they examined how its components shaped the evolution of the universe. In the early cosmos, dark energy played almost no role. Matter was dense, and its gravitational influence was strong. Galaxies and clusters formed as matter collapsed under its own pull. Dark matter provided most of the gravitational scaffolding, drawing ordinary matter toward its concentrations. During this era, the universe behaved much as one would expect from a system dominated by attractive gravity. But as the universe expanded and matter became more thinly spread, the influence of dark energy grew increasingly important. Unlike matter, dark energy did not dilute. Its constant energy density meant that as space grew, dark energy occupied more volume without weakening. At some point, its influence began to rival that of matter, and eventually, it overtook it. This transition, occurring a few billion years ago, marked the moment when the universe shifted from deceleration to acceleration. The faint glow of distant supernovae recorded this transition, revealing a cosmic story that could not be told by matter alone. The remarkable success of the Lambda cold dark matter model encouraged scientists to test its predictions with increasing precision. Measurements of the cosmic microwave background revealed acoustic peaks whose positions and heights depended on the amounts of dark matter, ordinary matter, and dark energy present in the early universe. Large surveys of galaxies traced the growth of cosmic structure, providing a way to measure how matter clumped over time. Weak lensing studies mapped the distribution of mass across the sky, tracing the invisible framework shaped by dark matter. In each of these tests, the Lambda cold dark matter model remained consistent with the data. It was not a perfect model in every detail, but its broad structure matched observations better than any alternative proposed so far. Yet even as the model succeeded, it carried a quiet tension. The cosmological constant worked, but it offered no explanation for its own value. It behaved as if space possessed a fixed energy density, yet theoretical calculations of vacuum energy predicted values that were unimaginably larger. If the vacuum truly contained such a huge energy density, the universe would have expanded so quickly that no structures could form. Instead, the vacuum energy that appears in cosmology is so small that its existence seems almost miraculous. This mismatch between theory and observation is sometimes described as one of the most significant unsolved problems in physics. Cosmologists did not ignore these puzzles. they sought ways to test whether dark energy might vary across time, perhaps evolving slowly rather than remaining constant. To explore this possibility, they measured the equation of state parameter with increasing accuracy. Any deviation from -1 would signal that dark energy was more complicated than the cosmological constant. But so far, the data have shown remarkable consistency with the value predicted by a constant energy density. This consistency does not prove that the cosmological constant is the final explanation, but it strengthens the case for its role as the simplest model that fits the current evidence. As researchers studied dark energy, they also examined how it interacted with the other components of the universe. Dark matter clumped to form structures, while dark energy smoothed those structures over cosmic scales. Ordinary matter flowed into the gravitational wells carved by dark matter, eventually forming stars and galaxies. Radiation carried imprints of the earliest moments of cosmic history, preserving information about the universe's composition. Each of these ingredients played a role in shaping the cosmos, and each influenced the others in subtle ways. The Lambda cold dark matter framework provided a coherent way to describe these interactions, yet it remained clear that this framework was a description, not an explanation. The success of the model did not diminish the mystery, it sharpened it. Why should the universe contain this mixture of components? Why should dark energy dominate only now and not earlier? Why should dark matter outweigh ordinary matter by a factor of more than 5? These questions revealed that while cosmology had become extraordinarily precise, it still grappled with profound unknowns. The model worked because it fit the data, but it did not explain why the cosmos had chosen such a configuration. It answered how the universe behaved, but not why it was built this way. And so, as Part 2 draws to a close, the universe stands revealed in extraordinary detail, yet cloaked in deep mystery. The Lambda cold dark matter framework is a triumph of observational cosmology, but its ingredients remain enigmatic. The next step in this journey is to confront the greatest theoretical puzzle of all, the cosmological constant problem, a riddle that emerges directly from the attempt to connect gravity with the quantum nature of empty space. The more the Lambda cold dark matter model proved its power to explain the universe, the more it illuminated a question that had lingered quietly beneath the surface of modern physics. If the cosmological constant truly represented a constant energy density filling empty space, then its value was astonishingly small, far smaller than anything predicted by quantum theory. This realization gave rise to the cosmological constant problem, a puzzle that did not arise from observation, but from the attempt to reconcile the observed universe with the deepest structures of theoretical physics. To appreciate the weight of this problem, one must first understand how the concept of vacuum energy emerges in quantum field theory. In that framework, every field in nature, whether associated with light, electrons, or more exotic particles, has fluctuations even in its lowest energy state. These fluctuations are not artifacts of calculation. They are measured phenomena, as shown in effects like the Casimir force, where two metal plates placed very close together experience an attractive force because the quantum vacuum between them contains fewer allowed fluctuations than the surrounding space. These vacuum fluctuations imply that even empty space carries energy. Yet when physicists attempt to calculate the total vacuum energy predicted by these fluctuations, the result is enormous, far larger than anything compatible with the observed behavior of the cosmos. This mismatch is not a matter of small corrections or missing factors. The theoretical estimates exceed the measured value by amounts so great that they defy ordinary understanding. If quantum vacuum energy behaved as predicted by naive calculations, the universe would expand with such furious speed that galaxies, stars, and planets could never form. The fact that we exist, and that cosmic structures exist, demands that the vacuum energy driving cosmic acceleration must be tiny, and yet the calculations suggest something vastly larger. This gap between theory and observation remains one of the most profound challenges in modern physics. The cosmological constant in the Lambda cold dark matter framework is often used as a stand-in for this vacuum energy, but its observed value is so small that it seems to require an explanation beyond simple calculation. Some physicists wondered whether there might be a hidden symmetry that forces the vacuum energy towards zero, but such a symmetry has not been discovered. Others have explored the possibility that vacuum contributions cancel out through some unknown mechanism, leaving behind only the tiny residue that shapes cosmic acceleration. But these ideas remain speculative, and none have been confirmed. Despite these uncertainties, the Lambda cold dark matter model continued to guide observational cosmology. Scientists used it to predict how galaxies should cluster, how the cosmic microwave background should appear, and how the expansion rate should evolve across time. Each prediction was compared with data from telescopes and satellites, and each comparison refined the parameters of the model. The value of the cosmological constant became known with increasing precision, pinned down not by theory, but by the behavior of the universe itself. And as the measurements grew sharper, they continued to point toward a universe where dark energy contributed the majority of the total energy budget. This realization reshaped our understanding of cosmic history. In the earliest moments of the universe, matter and radiation dominated the dynamics. Structures formed under the pull of gravity. Galaxies grew from tiny fluctuations left over from the earliest times. But as the universe expanded, matter spread out more thinly. Its gravitational influence weakened. Meanwhile, dark energy, with its constant density, remained steady. At a certain point, the influence of dark energy surpassed that of matter, and the universe transitioned into an era of accelerated expansion. This transition, recorded in the light of distant supernovae, marked a turning point in cosmic evolution. The Lambda cold dark matter framework captured this transition elegantly, yet it did so without revealing the true nature of the energy responsible. The framework described how the universe behaved, but not why. It offered a map of cosmic expansion, but not the identity of the force steering it. The simplicity of the model made it powerful, but that simplicity also magnified the mystery. If dark energy was truly constant, why had its influence emerged only recently in cosmic history? If the universe had existed for billions of years, why had dark energy begun to dominate only at this particular epoch? This puzzle, sometimes called the coincidence problem, remained unresolved. Even as these questions deepened, the observational foundations of the model grew stronger. Precise measurements from the Planck satellite refined the values of the cosmological parameters with extraordinary accuracy. Large galaxy surveys traced the distribution of matter across vast volumes of the universe. Weak lensing studies revealed the subtle distortion of distant galaxies by intervening mass. Each new dataset added clarity, yet each also reinforced the same fundamental message. The universe was filled with far more than the matter we could see. Most of it was dark, most of it was unfamiliar, and a significant portion of it was something that seemed to act not through attraction, but through a gentle cosmic repulsion. The success of the Lambda cold dark matter framework displayed the power of combining observation with theory, but it also highlighted the limits of current understanding. Cosmologists had identified the ingredients of the universe with impressive precision, yet the nature of those ingredients remained elusive. Dark matter shaped the growth of structure, yet it had not been detected in any laboratory. Dark energy drove cosmic acceleration, yet its origin defied explanation. Even ordinary matter, despite being understood in detail, accounted for only a small fraction of the cosmic total. As Part 3 comes to a close, the stage is set for the next inquiry. The cosmological constant model works astonishingly well, but it also exposes a profound theoretical divide. The predictions of quantum theory and the requirements of cosmology stand at odds, separated by a gulf that has not yet been bridged. This gulf is the cosmological constant problem, a challenge that invites scientists to rethink the relationship between gravity, quantum fields, and the deepest nature of space. And so the story moves forward, toward the chapter where this problem is examined directly, revealing how the smallest scales of physics collide with the largest scales of the universe. The moment scientists accepted that the cosmological constant offered the simplest explanation for the universe's accelerating expansion, they stepped directly into one of the deepest and most perplexing mysteries in modern physics. The constant itself was not difficult to write into the equations of general relativity. It appeared naturally, as a term that modified the curvature of space and time. But once observations revealed that its value was real and non-zero, the simplicity of the mathematics collided with a profound theoretical puzzle. The value required to match the universe was so small, so finely tuned, that it stood in stark contrast to the predictions of quantum field theory. This tension became known as the cosmological constant problem, a puzzle that sits at the very boundary between our understanding of gravity and our understanding of the quantum world. To grasp the scale of the problem, one must first consider how quantum field theory treats empty space. In that framework, even a vacuum is never truly empty. Fields fluctuate constantly, producing energy that cannot be removed. These fluctuations give rise to measurable effects, such as the Casimir force between metal plates or the Lambda shift in atomic energy levels. Experiments confirm that the quantum vacuum contains energy. Yet when physicists attempt to calculate how much energy the vacuum should contain, the theoretical values overwhelm the tiny amount implied by cosmic acceleration. The difference between the theoretical predictions and the observed value is so vast that it represents one of the largest known mismatches between theory and measurement in all of physics. This problem did not arise because scientists misread the observations. The supernovae, the cosmic microwave background, the galaxy surveys, and the weak lensing measurements all pointed consistently toward a universe whose expansion was being driven by a constant and extremely small energy density. The issue lay within theory itself. Quantum field theory, successful in describing particles and forces at subatomic scales, predicted that the vacuum should have an energy density far larger than what cosmology required. If these theoretical estimates were correct, the universe would expand so rapidly that no structure could form. Instead, galaxies exist, stars exist, life exists. Reality itself contradicts the simplest theoretical predictions. This mismatch cast a long shadow across physics. Was the theory incomplete? Was something missing from our understanding of quantum fields? Was there an unknown mechanism that cancelled the vacuum energy almost perfectly, leaving behind only a tiny residue? Or did the cosmological constant represent something altogether different, a property of space-time not directly tied to quantum fluctuations? These questions arose not from philosophical speculation, but from the undeniable tension between observation and theory. The fact that the cosmological constant matched the data so well only sharpened the mystery. As scientists explored the implications of this puzzle, they recognized that the cosmological constant problem was not merely a matter of adjusting equations. It touched the foundations of physics. In quantum field theory, fields contribute energy even when they are in their lowest energy state. Each field adds to the total. The contributions can be enormous. To reduce these contributions to the tiny value inferred from cosmology would require cancellations so precise that they seemed unnatural. If such cancellations occurred, what principle enforced them? What symmetry or mechanism ensured that the vacuum energy did not overwhelm the universe? Some researchers proposed that the vacuum energy might not gravitate in the way simple theory predicts. Perhaps some aspect of gravity or quantum physics remained undiscovered. Others explored ideas involving new symmetries that could eliminate vacuum contributions. Yet these proposals faced serious challenges. Many required modifications to well-tested theories, and none offered a complete explanation consistent with all known data. Moreover, the problem remained intertwined with the deepest aspects of general relativity. In that theory, energy cannot simply be ignored. Anything with energy must contribute to the curvature of space-time. And the vacuum, with its quantum fluctuations, possesses energy. The cosmological constant problem became one of the most discussed puzzles in theoretical physics. It was a problem that did not yield to simple solutions. It resisted attempts to explain it through standard techniques, yet it stood at the center of the most successful cosmological model ever constructed. Physicists found themselves in a strange position. They had a model that described the universe with extraordinary accuracy, yet that model included a parameter whose value defied theoretical understanding. As the puzzle deepened, scientists began to examine the timing of dark energy's emergence in cosmic history. The universe is billions of years old, and for most of that time, matter dominated the dynamics. Gravity shaped the growth of galaxies and clusters. But in the last several billion years, dark energy began to dominate instead. Its influence rose as the universe expanded, eventually surpassing the gravitational pull of matter. This transition raised another question. Why did dark energy become important precisely at this epoch? Why not earlier? Why not later? This question became known as the coincidence problem, and it added another layer to the mystery. Despite these challenges, the cosmological constant remained the simplest explanation for acceleration. Its success in fitting the data could not be denied. But simplicity in modeling does not guarantee simplicity in reality. The universe often reveals truths that appear straightforward on the surface, but conceal profound depth beneath. The cosmological constant may be one such truth. A quiet, persistent energy woven into the structure of space, small enough to be nearly invisible for billions of years, yet powerful enough to shape the destiny of the cosmos. As Part 1 closes, the stage is set for a deeper exploration of how scientists confronted this puzzle. The next part of the chapter will trace the ways in which researchers attempted to test the nature of the cosmological constant, and how they searched for possible deviations that might reveal whether dark energy was truly constant or whether it hinted at new physics beyond the familiar framework. As scientists confronted the enormity of the cosmological constant problem, they found themselves compelled to probe the universe with sharper tools and deeper questions. If the cosmological constant truly represented a constant energy of the vacuum, then its behavior should be uniform across cosmic time. But if dark energy varied even slightly, if it shifted in strength or evolved with the expansion, the effects would ripple through the history of the cosmos in ways that could be observed. The task became clear. Researchers needed to test, with ever greater precision, whether dark energy was truly constant or whether it showed hints of change. To explore this, cosmologists turn to the equation of state parameter, a single number that describes the relationship between the pressure and energy density of dark energy. If dark energy was a pure cosmological constant, this parameter would take the value of -1. If it differed, even subtly, that difference would signal that dark energy had properties more complex than a simple constant. It might vary with time. It might arise from a new field. It might reflect physics beyond general relativity. But such variations could be detected only through precise measurements of how the universe expanded and how its structures grew. The supernova studies continued, expanding to include more distant events and improved light curve analyses. Each new observation offered a glimpse into the expansion history of the cosmos. The faintest and most remote supernovae carried the oldest messages, recording the universe as it was billions of years before the present epoch. If dark energy changed over time, the distances inferred from these ancient explosions would reflect that change. Yet as the data grew, the results remained remarkably consistent with the prediction of a constant equation of state parameter near -1. But supernovae were only one piece of the puzzle. Scientists broadened their approach to include a wide range of cosmological probes. One of the most important came from the cosmic microwave background. This ancient radiation carries signatures of the early universe that are exquisitely sensitive to its composition. The patterns of peaks and troughs in its temperature variations encode information about the total energy content, including dark energy. While the cosmic microwave background records the universe at a time long before dark energy dominated, its arrangement still constrains any models that attempt to describe the entire history of cosmic expansion. The measurements from satellites such as the Planck mission offered unmatched precision, reinforcing the idea that dark energy was consistent with a constant value. Another crucial line of evidence came from the study of baryon acoustic oscillations. These subtle imprints of primordial sound waves serve as a cosmic yardstick. By measuring the apparent size of this yardstick at different distances, astronomers can trace how cosmic expansion has unfolded over time. If dark energy changed with cosmic age, the scale of these oscillations would shift in ways that would be detectable. Large galaxy surveys mapped these oscillations across vast regions of space, offering independent measurements that could confirm or challenge the conclusions drawn from supernovae and the cosmic microwave background. Once again, the data aligned with the simplest interpretation. Dark energy behaved as if it were constant. Weak gravitational lensing provided a different perspective. Instead of tracing the expansion directly, it traced how matter clustered over time. As the universe expands more rapidly, the growth of cosmic structure slows. If dark energy varied, that variation would influence how galaxies and dark matter clumped together. Observations from wide-field surveys measured the tiny distortions in the shapes of distant galaxies, revealing the distribution of matter. These measurements supported the same conclusion that emerged from the other probes. Dark energy showed no clear signs of evolution. Its influence appeared steady, quiet, and persistent. As results from these diverse observations accumulated, scientists began to see the Lambda cold dark matter model not as a tentative idea, but as the best available description of cosmic behavior. It offered consistency across the supernova data, the cosmic microwave background, baryon acoustic oscillations, and weak lensing. Each method probed the universe in a different way, yet all pointed toward a common conclusion. Dark energy functioned like a cosmological constant, and its equation of state parameter hovered near -1. Yet this success sharpened the underlying mystery rather than resolving it. If dark energy were indeed constant, its value remained disturbingly small and inexplicable. If it varied, the variations were too subtle for current instruments to detect. The universe offered no simple answer. It revealed a constant influence shaping its expansion, yet provided no insight into the origin of that influence. Scientists explored the possibility that dark energy might interact with dark matter, exchanging energy in ways that could alter cosmic behavior. They considered whether dark energy might arise from a new kind of field permeating space, one that evolved so slowly that its changes were nearly invisible. They examined modifications to general relativity, theories in which the equations governing gravity differed at large scales. But each idea faced stringent observational tests, and most variations either conflicted with data or required assumptions that lacked independent support. The cosmological constant problem remained as formidable as ever. It was not simply a question of adjusting numbers. It was a challenge that touched the foundations of quantum field theory, the nature of spacetime, and the origins of cosmic expansion. Even as the Lambda cold dark matter framework succeeded across observations, its reliance on a parameter so poorly understood remained a reminder of how much science has yet to uncover. Still, the effort to test the constancy of dark energy had taken cosmology into a new era, one marked by unprecedented precision and a deeper connection between theory and observation. The next part of the chapter would explore the broader consequences of this problem, revealing how the clash between quantum predictions and cosmological measurements led physicists to question the very nature of vacuum energy and the structure of spacetime. As scientists pressed deeper into the implications of the cosmological constant problem, they came to recognize that they were confronting something more fundamental than a mismatch between numbers. They were encountering a tension between two of the most successful frameworks in all of physics. On one side stood general relativity, Einstein's profound description of gravity as the geometry of spacetime. On the other stood quantum field theory, the foundation of particle physics, and the mathematical language that describes the behavior of every known quantum field. Each of these theories had been tested to extraordinary precision. Each had reshaped our understanding of the universe. Yet when they were brought together to describe something as conceptually simple as the energy of the vacuum, they resisted harmonization. The cosmological constant problem became the visible seam where these two worldviews met and refused to fully align. One of the central issues lay in the way quantum field theory assigns energy to empty space. According to the theory, every quantum field contains fluctuations even when it is in its lowest energy state. These fluctuations contribute to the vacuum energy density. But when physicists calculate this energy using the natural cutoff scales that arise in quantum field theory, the results are immense. These calculations imply that the vacuum energy should be many orders of magnitude larger than what cosmology observes. If this theoretical vacuum energy were inserted into the equations of general relativity, the resulting expansion would be so extreme that the universe would have torn itself apart almost instantly after the Big Bang. Clearly, something was wrong. Either the vacuum energy did not gravitate in the expected way, or the theoretical calculations were incomplete, or there existed an unknown mechanism that suppressed the vacuum energy to the tiny value inferred from observations. Physicists searched for solutions within the language of symmetry, one of the guiding principles of modern theoretical physics. Many of the most successful ideas in particle theory arise from symmetries that constrain the behavior of fields. Perhaps a symmetry existed that forced the vacuum energy to be small. Yet no known symmetry accomplished this in a natural way. Some explored the possibility that the vacuum energy of different fields might cancel out. But such cancellations would need to be precise beyond anything seen elsewhere in physics. Even the slightest deviation from perfect cancellation would produce a vacuum energy far larger than cosmology allowed. These theoretical attempts, while creative, did not produce a stable resolution to the problem. Others proposed that the cosmological constant might arise from a deeper structure of spacetime, one not captured by simple quantum field theory. Perhaps the vacuum energy predicted by quantum theory was not the same energy that influenced gravity. Perhaps some aspect of spacetime filtered out the large quantum contributions, leaving behind only the tiny portion responsible for acceleration. But these ideas remained speculative, and no experimental evidence supported them. The problem persisted, unyielding and mysterious. As theorists struggled with this puzzle, observers continued to push the limits of what could be measured. The more precisely the expansion of the universe was charted, the more confidently cosmologists could assert that dark energy behaved like a constant. The more accurately the cosmic microwave background was mapped, the more tightly the cosmological parameters were constrained. The more galaxy surveys expanded, the more clearly the large-scale structure of the universe revealed its shape. All of these observations reinforced the need for a constant energy density, yet none shed light on its origin. The coincidence problem further deepened the mystery. Why should dark energy become dominant precisely during the era when intelligent observers are able to measure it? Billions of years earlier, when galaxies were forming, dark energy had almost no influence. Billions of years from now, dark energy will dominate even more strongly. Yet in the present cosmic moment, dark energy and matter contribute comparable amounts to the total energy density. This balance is fleeting on cosmic timescales, and no known physical mechanism explains why we live during such a brief transitional epoch. The coincidence problem did not undermine the observations, but it underscored the sense that our understanding of the universe was incomplete. Amid these mysteries, the Lambda cold dark matter model continued to guide the study of cosmic evolution. It provided a framework for interpreting the data and a foundation for exploring new ideas. But scientists remained aware that this framework might be only a temporary step toward a deeper theory. The cosmological constant problem hinted that something profound was missing from the current picture. It suggested that the true nature of empty space might be far more complex than either general relativity or quantum field theory described. To solve the problem, physicists would need to explore the interface between gravity and quantum physics, two realms that had long resisted unification. These explorations led to theories that extended beyond the standard frameworks, including ideas about modified gravity, extra dimensions, or emergent spacetime. None of these ideas were established. All remained active areas of investigation. But the cosmological constant problem served as a compass, pointing toward the regions of theoretical physics where answers might eventually be found. It was both a challenge and a guide, urging scientists to push beyond the limits of current knowledge. Yet despite the difficulty of the problem, the observations themselves remained steady and clear. Dark energy behaved as if it were constant. The cosmological constant remained the simplest explanation. The mismatch between theory and observation remained unresolved, and the tension between general relativity and quantum field theory persisted, waiting for a deeper theory to reconcile them. As this chapter closes, the foundations of the mystery stand fully revealed. The universe is expanding at an accelerating rate, driven by an energy whose origin we do not yet understand. The cosmological constant problem exposes the gap between our understanding of the quantum world and the cosmic world. It challenges us to rethink the nature of empty space. And it sets the stage for the next chapter, where scientists attempt to test gravity itself on cosmic scales, searching for clues that might lead to a deeper explanation. The discovery of cosmic acceleration forced scientists to re-examine not only the nature of dark energy, but the very foundation of the laws that describe the universe. General relativity had guided physics for more than a century, tested with extraordinary precision in the solar system, in the motion of planets, in the timing of binary pulsars, and in the ripples of gravitational waves. Its predictions had been confirmed again and again, often to many decimal places. Yet the accelerating universe raised a question that could not be ignored. Could general relativity, so successful in familiar environments, behave differently when stretched across the enormous scales of the cosmos? The laws that shape the orbit of Mercury, or the merger of neutron stars, might not reveal everything about the laws that govern galaxies separated by millions of light years. To explore this possibility, scientists had to examine gravity in a way that was both delicate and ambitious. They needed to test the large-scale predictions of general relativity against the behavior of the universe itself, not through laboratory experiments, but through the intricate patterns written into cosmic structure. The challenge was immense. Gravity on the scale of galaxies and clusters is shaped not only by matter, but by the expansion of space. The forces at work are subtle, interconnected, and influenced by the hidden presence of dark matter. Testing gravity at cosmic scales required the careful disentangling of these effects, a task that demanded both precise measurements and sophisticated models. Even before the discovery of acceleration, researchers had considered alternative theories of gravity. Some sought to explain galactic rotation curves without invoking dark matter. Others attempted to modify Einstein's equations to account for cosmic behavior. These ideas took many forms. Some proposed that the curvature of spacetime responded differently at large scales. Some introduced new fields that coupled to gravity. Others imagined that the universe contained additional dimensions beyond the familiar three of space and one of time. While none of these theories gained universal acceptance, they remained active areas of study, especially in light of the mysteries introduced by dark energy. After acceleration was discovered, the motivation to test gravity on cosmic scales sharpened. If dark energy was not a cosmological constant, then perhaps it arose from modifications to general relativity. In this view, the universe might accelerate not because space contained a mysterious energy, but because the laws of gravity behaved differently at vast distances. To investigate this, scientists needed to use observations not just of distances, as in the supernova studies, but of how cosmic structures grew over time. The growth of galaxies and clusters is governed by gravity. If gravity were modified, the growth rate would deviate from the predictions of general relativity. The key lay in two quantities that could be measured independently. One was the expansion history of the universe, which recorded how distances changed over cosmic time. The other was the growth rate of cosmic structure, which tracked how matter clumped together under the pull of gravity. General relativity provided a specific relationship between these two quantities. If observations revealed a mismatch between the predicted and observed connection, it would signal that gravity behaved differently from Einstein's expectation. This approach required precise data. Scientists relied on wide-field surveys that mapped the distribution of galaxies across enormous volumes of space. These surveys revealed how galaxies clustered, how filaments stretched across the cosmic web, and how voids opened between structures. The shape and amplitude of these patterns preserved information about the strength of gravity over billions of years. If gravity were weaker or stronger on large scales, the structure of the cosmic web would reflect that difference. Weak gravitational lensing offered another crucial tool. As light travels from distant galaxies toward Earth, it is bent slightly by the gravitational fields of intervening matter. These tiny distortions, when measured across millions of galaxies, created maps of the underlying mass distribution. Lensing provided a way to probe gravity directly, without relying on assumptions about how galaxies trace dark matter. If modified gravity theories were correct, the patterns of lensing would differ from those predicted by general relativity. Multiple surveys, including the Dark Energy Survey and the Kilo Degree Survey, contributed lensing measurements that allowed scientists to compare theory and observation with remarkable precision. Meanwhile, the behavior of galaxies in redshift space offered yet another window into cosmic gravity. As galaxies move through space, their velocities create small distortions in their redshift measurements. These distortions, known as redshift space distortions, carry information about how matter flows under the influence of gravity. By analyzing these patterns, scientists could measure the rate at which structures grew. Again, any deviation from the predictions of general relativity would reveal itself in these motions. Throughout these efforts, general relativity continued to hold strong. The expansion history, measured by supernovae and baryon acoustic oscillations, matched its predictions. The growth rate of structure inferred from lensing and galaxy clustering remained consistent with its expectations. While some anomalies appeared, they were often small, and it remained unclear whether they pointed toward new physics or simply reflected the limits of current observations. The universe, in its vastness, offered no immediate sign that gravity behaved differently at cosmic scales. Yet the effort to test general relativity remained essential. The presence of dark energy, whatever its nature, demanded that scientists push beyond familiar territory. If gravity differed from Einstein's theory, even slightly, the signs would be encoded in the precise relationship between cosmic expansion and structure growth. And even if general relativity continued to match observations, the very act of testing it deepened our understanding of the universe and clarified the boundaries within which the theory remained valid. As this part draws to a close, the stage is set for further exploration. The universe had revealed its accelerated expansion. The Lambda cold dark matter framework offered a powerful model for interpreting the data. But the question remained open. Was dark energy a property of space, or was it a sign that gravity itself changed across cosmic scales? The next part of the chapter would explore these theoretical possibilities, showing how scientists constructed models that attempted to modify gravity while preserving the successes of general relativity on smaller scales. As scientists ventured deeper into the possibility that gravity itself might behave differently across the vast reaches of the cosmos, they began to explore theoretical frameworks that modified Einstein's equations in subtle and controlled ways. These attempts did not arise from a desire to discard general relativity, but from a recognition that even the most successful theories may have limits when extended to unfamiliar domains. General relativity had been tested with exquisite precision in the solar system and in the motion of binary pulsars. The detection of gravitational waves from colliding black holes confirmed its predictions in some of the most extreme environments known. Yet the accelerating expansion of the universe hinted that something more might be at play when gravity stretched across scales of millions or billions of light years. One of the earliest classes of modified gravity theories explored how the curvature of spacetime might respond differently under specific conditions. In these theories, the gravitational action, which determines how spacetime evolves, was altered by adding new terms that depended on the curvature. These frameworks extended general relativity in a mathematically consistent way, reducing to the familiar equations in strong gravitational fields or in regions where curvature was small. They aimed to preserve the success of general relativity while providing a possible explanation for cosmic acceleration without invoking dark energy. However, these modifications had to meet strict observational constraints. If the curvature terms altered gravity too strongly, they would disrupt the behavior of stars, planets, or galaxies. If they altered it too weakly, they would fail to explain acceleration. Another approach introduced new fields that interacted with gravity. These scalar tensor theories added an additional scalar field alongside the metric that described spacetime. The scalar field influenced gravity by modifying how masses attracted each other over large distances. In dense environments such as within galaxies or the solar system, the scalar field could be suppressed, allowing general relativity to remain accurate. But on cosmic scales, where matter was more thinly distributed, the field could influence the expansion of the universe. These ideas captured the imagination of theorists because they offered a means to produce acceleration naturally through the dynamics of the scalar field. Yet these models also face the challenge of matching observations across multiple cosmic probes. Any departures from general relativity needed to be subtle enough to avoid conflicting with the cosmic microwave background, galaxy clustering, or lensing measurements. Additional theories explored the possibility that the universe might contain extraspatial dimensions. These ideas were motivated by attempts to unify gravity with the other fundamental forces. If gravity could propagate through dimensions beyond the familiar three, its strength might change with distance in ways that could influence cosmic expansion. Such theories predicted that gravity would behave differently at large scales, potentially leading to acceleration. Yet they too faced constraints from observations of the cosmic microwave background and galaxy surveys. Any theory that altered gravity too dramatically would disrupt the delicate balance of cosmic structure, producing predictions inconsistent with the data. Regardless of the specific approach, all modified gravity theories confronted the same fundamental challenge. They had to reproduce the successes of general relativity in the solar system and in strong gravitational fields, while also offering new behavior on cosmic scales. Achieving both simultaneously required mechanisms that allowed gravity to transition smoothly between different regimes. These transition mechanisms were known as screening effects. In regions of high density, such as near stars or planets, the additional effects of modified gravity would be suppressed, leaving Einstein's predictions intact. In low-density regions, such as the large-scale structure of the universe, the additional effects could emerge and influence the cosmic expansion. Scientists tested these theories using the full range of observations available. Weak gravitational lensing offered insight into how mass was distributed and how gravity bent light across vast distances. Redshift space distortions provided information about how galaxies moved under the influence of gravity. Baryon acoustic oscillations traced the large-scale geometry of the universe. The cosmic microwave background recorded the earliest moments of cosmic history. Each of these tools placed constraints on modified gravity theories. If a theory predicted too much clustering or too little lensing, it could be ruled out. If it predicted a growth rate of structure incompatible with observations, it lost viability. Through this process, many models were refined, while others were discarded. The effort to test gravity on cosmic scales revealed something remarkable. While modified gravity theories offered creative ways to mimic the effects of dark energy, none yet provided a better fit to the full suite of cosmological data than the Lambda cold dark matter framework. In many cases, the simplest explanation remained the most successful. The cosmological constant, despite its theoretical challenges, matched the observations with impressive consistency. Modified gravity theories continued to be explored, not because they outperformed the standard model, but because they offered valuable insights into the limits of general relativity and the possible paths to a deeper understanding of cosmic dynamics. Still, the search for deviations from general relativity remained essential. Scientists recognized that the universe might hide subtle differences that appeared only on the largest scales. If these differences existed, they would reveal themselves in the relationship between cosmic expansion and the growth of structure. The beauty of this approach lay in its independence from theoretical assumptions. The universe itself provided the experiment, written across billions of years of cosmic evolution. As Part 2 comes to a close, the investigation into gravity's behavior stands at a pivotal moment. Modified gravity theories continue to offer intriguing possibilities, yet the observational evidence remains most consistent with general relativity and the cosmological constant. The story now moves toward a deeper examination of how these observational tests are carried out, how they reveal the laws of the universe, and how they shape our understanding of what may lie beyond the familiar framework. As the search for a deeper understanding of gravity advanced, scientists recognized that the universe itself had become a vast laboratory. Unlike experiments on Earth, which can only test gravity over limited distances and strengths, the cosmos offered a dynamic environment where gravity acted across unimaginable scales. Galaxies clustered into filaments stretching millions of light years. Clusters collided in titanic mergers. Light traveled through regions filled with dark matter, whose presence could be inferred only by the way it bent light and guided galaxies. This grand cosmic stage became the testing ground for ideas that sought to determine whether general relativity remained exact or whether it required subtle modifications. One of the most powerful methods for probing gravity involved studying the interplay between the expansion of the universe and the growth of cosmic structure. In general relativity, these two quantities are intimately linked. When the universe expands more rapidly, the growth of structure slows. Matter has less time to collapse under its own gravity. If dark energy causes the expansion to speed up, the formation of galaxies and clusters becomes less efficient. This relationship is not a rough guideline, but a precise mathematical prediction. Any deviation from this relationship would reveal that gravity behaved differently on cosmic scales. To investigate this, scientists built surveys that mapped the distribution of galaxies with unprecedented depth and breadth. These surveys measured how galaxies clustered on different scales and at different epochs of cosmic history. The patterns of clustering preserved a record of how gravity had acted over billions of years. A universe governed by modified gravity would leave distinct signatures in the way structures evolved. These signatures would appear in the strength of clustering, the shapes of voids, and the statistical correlations between galaxies. By comparing these measurements with theoretical predictions, astronomers could test the limits of general relativity on the largest scales. Weak gravitational lensing provided another essential window into cosmic gravity. As light from distant galaxies passed through the large-scale structure, it was deflected by the gravitational fields of intervening matter. This deflection was extremely subtle, often distorting the shapes of background galaxies by only a small fraction. But when millions of galaxies were studied collectively, the distortions formed patterns that revealed the distribution of mass. Weak lensing did not depend on how galaxies formed or how they emitted light. It depended only on gravity. As such, it became one of the most direct ways to test whether general relativity held true across cosmic distances. Lensing studies from the Dark Energy Survey, the Kilo Degree Survey, and other wide-field programs showed that the universe's matter distribution largely followed the predictions of general relativity. Yet some tensions emerged, small hints that the observed growth of structure might be slightly lower than expected. These differences did not immediately imply new physics. They might reflect statistical fluctuations or limitations of current models. But they reminded scientists that even the most successful theories must be tested repeatedly, especially when the universe reveals puzzles as deep as dark energy. Another key observational tool involved measuring redshift space distortions, the apparent distortions in galaxy positions caused by their peculiar velocities. These velocities arose from the gravitational pull of surrounding structures. By analyzing the statistical patterns of these distortions, scientists could determine how quickly matter was flowing toward regions of higher density. This flow depended sensitively on the nature of gravity. If gravity were modified, the rate of inflow would differ from the predictions of general relativity. Measurements from surveys such as the Baryon Oscillation Spectroscopic Survey and its successors helped refine these tests, providing complementary constraints on gravity's behavior. The cosmic microwave background offered yet another layer of insight. While it recorded the universe during its early stages, the way its photons were deflected by large-scale structure on their journey to Earth preserved information about gravity across billions of years. By studying the lensing of the cosmic microwave background, scientists could map the distribution of dark matter and test the predictions of general relativity. These measurements, combined with galaxy surveys and lensing studies, created a multi-layered picture of cosmic gravity. Through all these efforts, one conclusion gradually took shape. While it was possible to construct modified gravity theories that produced acceleration without dark energy, these theories struggled to match the full suite of observations. They could sometimes explain one dataset, but they often failed when confronted with another. The simplest explanation, the cosmological constant within general relativity, continued to provide the most consistent and accurate fit. This did not diminish the importance of testing gravity. On the contrary, it revealed how essential such tests were. The accelerating universe demanded that scientists explore every possibility, even those that seemed unlikely. Each constraint strengthened the confidence in general relativity. Each anomaly, however small, reminded researchers to remain vigilant. The universe was vast enough to hide surprises, and the interplay between gravity and cosmic expansion remained one of the deepest mysteries in modern science. What emerged from this journey was a renewed appreciation for both the strength and the limitations of current theory. General relativity continued to shine as one of the most successful theories ever created. But the presence of dark energy meant that the theory was incomplete. It described how the universe evolved, but not why it contained a component that drove acceleration. Modified gravity theories provided valuable insights, yet they could not surpass the predictive power of the standard model. The result was a landscape rich with questions and alive with possibilities. As this chapter concludes, the path forward becomes clear. To understand cosmic acceleration, scientists must look not only to gravity, but to the way the universe reveals its laws through the patterns of light, matter, and structure. The next chapter will turn to these observational forensics, showing how the cosmos itself offers the clues needed to uncover the nature of its most mysterious forces. The universe does not speak to us with words, yet it leaves behind traces that can be read with patience, precision, and imagination. Every beam of light, every shift in wavelength, every subtle distortion in the shapes of distant galaxies carries information about the forces that shaped it. To uncover the nature of cosmic acceleration, astronomers turn to these clues with the mindset of investigators unraveling a mystery. They approach the cosmos as a vast crime scene, filled with evidence left scattered across billions of years of expansion. The question was simple to ask, but enormously difficult to answer. What combination of ingredients and laws could produce the universe we see today? The first and most direct clue came from the expansion of space itself, traced through the redshift and brightness of distant objects. But as powerful as the supernova technique had been in revealing acceleration, it was only one piece of a much larger puzzle. To identify the true nature of dark energy or to detect any deviations from general relativity, scientists needed to gather independent lines of evidence, each probing a different aspect of the universe. Like different witnesses recounting the same event from different angles, these observations had to converge on a consistent story if they were to reveal the truth. One of the most important of these witnesses was the cosmic microwave background, the ancient glow left over from a time when the universe was hot, dense, and filled with a primordial plasma. This radiation, now cooled to just a few degrees above absolute zero, carried imprints of sound waves that once rippled through the early cosmos. The temperature variations recorded by satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck mission provided a snapshot of the universe when it was only a few 100,000 years old. From this snapshot, scientists could infer the total amount of matter, the density of baryons, the density of dark matter, and the presence of dark energy. Although dark energy did not dominate the early universe, its influence on the overall geometry left unmistakable clues in the cosmic microwave background. As these early universe measurements were compared with observations of the present-day cosmos, a remarkable story began to unfold. The universe appeared nearly flat, a property that required a specific balance between matter, radiation, and dark energy. The cosmic microwave background provided the earliest chapter of this story. To uncover the middle chapters, astronomers turned to a feature imprinted in the large-scale structure of the universe known as the Baryon Acoustic Oscillation Scale. This scale originated from the same sound waves that once pulsed through the early plasma. When matter and radiation decoupled, these ripples left behind a preferred clustering scale in the distribution of galaxies. By measuring this scale at different redshifts, scientists could trace how distances in the universe changed over time. The Baryon acoustic oscillation method became one of the most robust tools for studying cosmic expansion. It provided a yardstick that did not depend on the complex physics of supernova explosions and did not rely on the detailed modeling of galaxy evolution. Instead, it offered a measurement rooted in the early universe and preserved across billions of years. Large surveys like the Baryon Oscillation Spectroscopic Survey mapped millions of galaxies, revealing a faint but persistent ripple pattern that served as a cosmic ruler. When the observed scale was compared with the predictions of cosmological models, it consistently supported the presence of dark energy and offered an independent confirmation of acceleration. Yet even these two powerful methods were not enough to fully unravel the nature of cosmic acceleration. Scientists needed a probe that measured not just distances, but the way matter moved under the influence of gravity. This brought them to the study of redshift space distortions, a phenomenon that arises because galaxies do not simply follow the flow of cosmic expansion. They also drift toward regions of higher density, pulled by the collective gravity of surrounding matter. These peculiar velocities distort the apparent positions of galaxies when their redshifts are measured. By analyzing the statistical patterns of these distortions, scientists could determine how quickly matter was clumping together over time. This growth rate of structure provided a test of gravity that was independent of the expansion history. In general relativity, the growth rate is linked to the expansion rate in a specific way. If gravity behaved differently at cosmic scales, or if dark energy evolved in time, the connection between growth and expansion would shift. By comparing the observed growth rate with the predictions of general relativity, scientists could test whether gravity remained unchanged across billions of years. Observations from surveys such as the extended Baryon Oscillation Spectroscopic Survey helped refine this measurement, revealing a picture broadly consistent with the Lambda cold dark matter model. Still, the cosmos offered more clues. Weak gravitational lensing, the slight bending of light by mass, provided a direct way to map the distribution of matter across the sky. While strong lensing creates dramatic arcs and multiple images, weak lensing produces distortions so small that they can be detected only by averaging the shapes of millions of distant galaxies. These distortions encode information about the underlying mass distribution and the strength of gravity. Surveys like the Dark Energy Survey and the Kilo Degree Survey measured these patterns with increasing precision. The results generally supported the predictions of general relativity, though they hinted at mild tensions in the growth of structure, inviting further scrutiny and deeper investigation. Cluster abundances offered yet another layer of evidence. Galaxy clusters are the largest gravitationally bound structures in the universe. Their number and distribution depend sensitively on the growth of matter. If dark energy slowed the formation of clusters, fewer clusters would form at later times. By counting clusters across different epochs and measuring their masses through lensing and X-ray observations, scientists could trace the evolution of structure in yet another independent way. These measurements added richness to the cosmic picture and provided an important cross-check on other methods. As all these observations accumulated, a powerful and intricate tapestry of evidence emerged. The cosmic microwave background revealed the initial conditions. Baryon acoustic oscillations mapped the geometry of space. Redshift space distortions measured the flow of matter. Weak lensing traced the invisible scaffolding of dark matter. Supernovae mapped the expansion history. Cluster counts tracked the buildup of structure. Together they formed a consistent story. The universe was expanding, and that expansion was accelerating. The simplest model that fit all the data remained the Lambda, cold, dark matter framework. Yet this harmony did not diminish the mystery. Instead, it highlighted how carefully the universe needed to be studied to uncover its secrets. The clues were subtle, the signals were faint, the patterns were etched into light that had traveled across billions of years. But each measurement brought scientists closer to understanding the nature of cosmic acceleration and the forces that shape the universe on its largest scales. As Part 1 closes, the cosmic investigation deepens. The tools of observational forensics reveal a universe rich with information, yet still guarded in its secrets. The next part will continue this journey, exploring how these observations intertwine to test the very foundations of gravity and hint at the possible paths beyond our current understanding. As scientists compared the many strands of observational evidence, they began to see how each dataset illuminated a different face of the same cosmic mystery. The expansion history revealed how distances changed over time. The growth of structure revealed how matter responded to gravity. The cosmic microwave background offered a snapshot of the primordial universe, while galaxy surveys traced its evolution across billions of years. Weak lensing revealed the hidden distribution of dark matter. Baryon acoustic oscillations measured the stretching of space. Together, these clues formed a complex network of information that allowed scientists not only to describe the universe, but to test its laws in ways that would have been impossible only a few decades earlier. Yet this process was not simple. Each observation required enormous care, from the precise calibration of instruments to the subtle modeling of astrophysical processes that could distort signals. A weak lensing measurement, for example, depends on the ability to measure the shapes of distant galaxies with exquisite accuracy. But those shapes can be affected by the atmosphere, by telescope optics, by detector noise, and by the galaxy's own structures. Astronomers developed sophisticated techniques to model these effects, ensuring that the faint imprint of gravity was not confused with artifacts of observation. This effort demanded collaboration between theorists, observers, and instrument designers, each contributing to the delicate balance between uncertainty and precision. Redshift surveys face challenges of their own. The redshift of a galaxy encodes both the stretching of space and the galaxy's own motion through the gravitational landscape. Separating these two influences required deep statistical analysis. Scientists examined millions of galaxies to extract patterns in their clustering, using the collective behavior of vast numbers of objects to unveil the underlying physics. The cosmic web, with its filaments, clusters, and voids, became a living record of gravity's influence. When compared with simulations based on general relativity, the observed structure traced the same patterns, the same rhythms of collapse and expansion that theory predicted. Simulations themselves played a critical role in this endeavor. Modern numerical models recreated the universe from its earliest moments to the present day, allowing scientists to follow the formation of galaxies and clusters under the influence of gravity, dark matter, and dark energy. These simulations required enormous computational power. They tracked the motions of billions of particles representing dark matter, evolving them under physical laws for billions of years of cosmic time. The result was a virtual universe, one that could be compared directly to observations. If the simulated universe matched the observed one, confidence grew in the underlying physics. If it diverged, theorists looked for the source of the discrepancy. These simulations revealed something remarkable. When they incorporated the parameters of the Lambda cold dark matter model, including a cosmological constant, they produced cosmic structures that mirrored those seen in the sky. Galaxies formed along filaments, clusters emerged at their intersections, and voids expanded between them. The model's predictions were not vague approximations. They were detailed and quantitative, matching the statistical distribution of galaxies across vast regions of space. This level of agreement strengthened the case that the universe's acceleration could indeed be explained by a simple cosmological constant. Yet the effort to test gravity did not end with agreement. Scientists sought out regions where theoretical predictions and observations seemed to diverge, no matter how small the difference. These tensions, even if subtle, represented opportunities to probe the edges of understanding. One such tension emerged in measurements of the growth of structure. Some, weak, lensing surveys suggested slightly less clustering than predicted by the Lambda cold dark matter model. These results were not large discrepancies, but they persisted across multiple datasets. Scientists considered whether these differences pointed toward new physics, or whether they arose from systematic effects not yet fully accounted for. The cosmic microwave background also offered subtle tensions, especially in the inferred value of certain parameters when compared with late-time measurements. While the overall picture remained consistent, these small inconsistencies prompted deeper scrutiny. Scientists revisited calibration methods, refined their models of astrophysical foregrounds, and compared results across multiple instruments. Each step reduced uncertainty and clarified the boundaries of agreement. Despite the richness of these observations, the cosmos remained generous in the depth of its information. Light from distant quasars revealed how matter was distributed along the line of sight through measurements of the Lyman alpha forest. Gravitational waves hinted at new ways to measure cosmic expansion by using black hole and neutron star mergers as standard sirens. Galaxy cluster masses could be inferred through X-ray observations, allowing comparisons with lensing measurements. Each method tested cosmic gravity from a different angle, and all contributed to a growing picture of precision cosmology. In this intricate network of observations, a guiding principle emerged. No single measurement could determine the nature of dark energy or the behavior of gravity. Only by combining independent probes could scientists disentangle the overlapping influences of matter, radiation, and cosmic expansion. This approach, known as multiprobe cosmology, became a defining feature of modern research. By requiring that all probes align within a consistent framework, scientists ensured that their conclusions rested on solid, interconnected foundations. As these efforts unfolded, the universe revealed itself not through grand declarations, but through quiet coherence. The expansion history, the growth of structure, and the cosmic geometry all pointed toward a universe shaped by dark matter and dark energy, with gravity behaving according to general relativity across the vast expanse. Yet the possibility of new physics remained alive. The faint hints of tension, the unresolved nature of the cosmological constant, and the limits of current instruments all pointed toward the need for deeper investigation. The next generation of surveys, telescopes, and space missions would push the boundaries even further, offering higher resolution, larger datasets, and more sensitive measurements. But before turning to the future, the present chapter continues its exploration in Part 3, bringing together the lessons learned from the cosmos and revealing how these observational tools collectively constrain the laws that govern the universe. As the many strands of cosmological evidence were woven together, scientists found themselves in possession of something extraordinary. They held a framework capable of describing the broad history of the universe, yet they also held the tools to test the validity of that framework in exquisite detail. Each observation, each dataset, each subtle distortion in the shape of a distant galaxy acted like a fingerprint of the laws that governed the cosmos. By studying these fingerprints, scientists could ask questions that had once seemed impossible. Did gravity truly follow the same rules across all scales? Did dark energy behave in a constant and unchanging way? Or did the universe contain hints of new physics that had only begun to reveal themselves? One of the central insights of this era of precision cosmology was the recognition that the universe could be tested using two fundamentally independent sets of measurements. The first set mapped how distances evolved, tracing the expansion of space through supernovae, baryon acoustic oscillations, and the cosmic microwave background. The second set measured how structures grew, revealing how matter collapsed under the pull of gravity through weak lensing, redshift space distortions, and cluster abundances. If these two sets of measurements aligned perfectly within the predictions of general relativity and the Lambda cold dark matter model, then the framework stood strong. If they diverged even slightly, it could signal the influence of new physics. This interplay between expansion and growth became one of the most compelling tools in modern cosmology. Observations of the expansion rate created a timeline of the universe's history, a record of how quickly space stretched from the earliest times to the present day. At the same time, measurements of the growth rate revealed how structures formed and evolved. These two stories had to match. If space expanded too quickly, structures would not have enough time to form. If gravity were too strong, structures would form too rapidly. The delicate balance between these forces preserved the universe as we observe it, and this balance provided a powerful way to test the laws that governed cosmic evolution. Even with this balance, the universe displayed subtle tensions that kept scientists alert. Some weak lensing measurements suggested that the clustering of matter was slightly lower than predicted. These hints were not decisive, but they encouraged researchers to examine the data more carefully, to refine their techniques, and to consider whether such differences might point toward a deeper truth. Perhaps the universe contained mild deviations from the simplest models. Perhaps some systematic effect in the measurements had not yet been fully understood. Or perhaps these small differences were the first indications of a new chapter in cosmology waiting to be uncovered. To explore these questions, scientists continued to expand their observational reach. They compared the behavior of galaxies in different environments. They examined clusters of galaxies at different points in cosmic time. They studied how light from distant quasars was absorbed by gas spread across billions of light years. They measured how the cosmic microwave background was lensed by intervening structures. Each piece of data enriched the picture, adding layers of complexity and nuance to the story of the cosmos. Through this growing network of observations, scientists also gained a deeper appreciation for the importance of precision. Even small uncertainties in the measurement of a supernova's brightness or a galaxy's redshift could influence the inferred properties of dark energy. The shape of a galaxy captured by a telescope had to be corrected for atmospheric blurring, detector imperfections, and intrinsic variations before its subtle lensing signal could be read. The large-scale clustering of galaxies had to be compared with simulations that accounted for complex astrophysical processes. Each step required meticulous attention, for the universe offered its clues quietly, and any misinterpretation could obscure their meaning. As the measurements grew more precise, the constraints on dark energy tightened. The equation of state parameter remained consistent with -1 to within a few percent, suggesting that dark energy behaved like a cosmological constant. Yet scientists remained vigilant. They understood that this apparent constancy could mask deeper complexity. Some models predicted that dark energy might vary so slowly that its evolution could escape detection until much more precise measurements were available. Others suggested that gravity might change only slightly on cosmic scales, with effects that accumulated slowly over billions of years. The challenge lay in distinguishing these subtle possibilities from the overwhelming success of the simplest model. The interplay between observation and theory deepened as cosmologists confronted these questions. To test the universe at the highest level, scientists developed statistical frameworks capable of combining diverse datasets while accounting for their uncertainties. They built models that allowed dark energy to vary in controlled ways, and tested those models against the data. They explored how modified gravity theories would influence the expansion history and growth rate, checking whether such theories produce signatures that could be compared with observations. Through this fusion of theory and measurement, the cosmological community gained insights not only into what the universe was doing, but into how precisely it could be described. Despite the extraordinary progress, the greatest mysteries remained untouched. The cosmological constant worked, yet its theoretical origin was unknown. Dark matter-shaped galaxies, yet its nature remained hidden. And the acceleration of the universe, so quietly revealed by distant supernovae, continued to challenge the deepest assumptions of physics. Observational forensics had succeeded in clarifying the universe's behavior, but they had not yet revealed the ultimate cause of that behavior. As this chapter draws to a close, it leaves a sense of both achievement and anticipation. The cosmos has been measured with unprecedented accuracy. Its structures have been mapped. Its history has been traced. Yet the fundamental question remains unanswered. What drives the acceleration of the universe? To search for answers, scientists must now turn to the realm of quantum fields and the puzzling nature of vacuum energy, where the smallest scales of physics collide with the largest scales of cosmology. Space often appears quiet, vast, and almost empty, but the emptiness that surrounds galaxies and clusters is not silent. At the quantum level, even the most seemingly desolate regions of the universe are alive with restless activity. A sea of fluctuations hums beneath the surface, creating a landscape where particles flicker in and out of existence, and where fields ripple with ceaseless motion. This is the quantum vacuum, a place that is never still, governed by the uncertainty principle and revealed through carefully measured experiments. And yet, for all we know about this hidden world, it poses one of the greatest mysteries in modern science. Why does its energy not tear the universe apart? The puzzle begins with the discovery that vacuum energy is not an abstract idea, but something that leaves measurable fingerprints in the physical world. In laboratories, the Casimir effect demonstrates that two metal plates placed extremely close together feel a force drawing them inward, a subtle push created by changes in the quantum vacuum between them. Other experiments, such as the measurement of the Lambda shift in hydrogen atoms, confirm that vacuum fluctuations influence the behavior of electrons and energy levels. These results show that the vacuum possesses energy, and that energy affects matter in ways that can be studied and quantified. But when theorists attempt to calculate the total amount of vacuum energy predicted by quantum field theory, the results become startling. The naive calculation produces a value so large that, if applied directly to the fabric of spacetime, the universe would expand with unimaginable violence. Galaxies, stars, planets, and even atoms could not form in such a universe. Yet the cosmos we observe is gentle and structured, expanding slowly at first, and accelerating only in recent cosmic time. The vacuum energy we infer from observations is incredibly small, many orders of magnitude below the theoretical prediction. This staggering mismatch is the cosmological constant problem, a challenge that has resisted all attempts at easy solution. Some theorists have suggested that symmetries in nature might cancel the enormous contributions predicted by quantum field theory, leaving behind only the tiny amount we observe. Supersymmetry once offered hope in this direction, but experiments have shown that if such a symmetry exists, it must be broken at energy scales too high to explain the observed smallness of the vacuum energy. Others have proposed that some unknown mechanism screens or regulates the vacuum contributions, so that gravity does not respond to them in the way general relativity predicts. Yet these ideas remain incomplete, unable to provide a consistent explanation that fits every observation. The puzzle grows even deeper when considering the history of the cosmos. In the early universe, matter dominated the gravitational landscape, slowing the expansion. Only in relatively recent cosmic time did the tiny vacuum energy begin to dominate, gently accelerating the expansion once more. This timing raises a profound question. Why should the densities of matter and dark energy be comparable only now, during the brief moment when observers like us exist? There is no known mechanism that naturally aligns these densities in this particular cosmic era. Despite the mystery, the observational evidence is clear. The cosmological constant provides a consistent description of the universe's acceleration. Measurements of distant supernovae, the patterns in the cosmic microwave background, and the clustering of galaxies all point toward a small, constant vacuum energy that shapes the large-scale geometry of space-time. The mystery lies not in the observation, but in the explanation, in the gap between what quantum field theory predicts and what the universe reveals. Quantum fields whisper one answer. Gravity whispers another. Somewhere between them lies a truth scientists have yet to uncover. The next chapter follows these whispers toward the emerging idea that space-time itself may arise from deeper principles of information, offering a new perspective on the nature of the universe. The search for the nature of cosmic acceleration leads inevitably to deeper questions about the fabric of space-time itself. General relativity portrays space-time as a smooth, continuous arena where matter and energy dictate curvature, and curvature dictates motion. Yet the strange behavior of quantum fields, the puzzle of vacuum energy, and the surprising thermodynamic properties of black holes hint that this picture may be incomplete. Beneath the smooth geometry described by Einstein's equations, there may lie a hidden network of relationships, woven not from matter or fields, but from information itself. The first hint of this deeper structure emerged from the study of black hole thermodynamics, when Jacob Bekenstein proposed that black holes possess entropy, proportional not to their volume, but to their surface area. It forced physicists to confront the idea that information in a region of space may scale with its boundary. Stephen Hawking's demonstration that black holes emit radiation strengthened this insight, revealing that black holes have a temperature and obey laws similar to those of ordinary thermodynamic systems. These discoveries suggested that the geometry of space-time might be intimately connected to the flow of information. This idea was later elevated by the holographic principle, which proposed that the physics within a region of space could be fully encoded on its boundary surface. Although this principle arose from theories far removed from the observable universe, its implications were profound. It pointed toward a universe where the apparent three-dimensional world may arise from underlying informational degrees of freedom, much as a hologram creates a three-dimensional image from a two-dimensional surface. The concept did not claim that our universe literally lives on a surface, but that the amount of information in any region is limited in a way that defies classical intuition. Further insights came from a remarkable theoretical framework known as the ADS-CFT correspondence. In this model, a gravitational theory in a higher dimensional spacetime can be exactly equivalent to a quantum field theory without gravity living on a lower dimensional boundary. This surprising duality demonstrated that geometry and quantum information are not independent concepts, but two faces of the same underlying structure. In this framework, the curvature of spacetime, the formation of black holes, and even the motion of particles emerged from the entanglement patterns within the quantum theory. This connection became even clearer through the study of entanglement entropy. The Ryu-Takayanagi formula revealed that the entanglement entropy of a region in the quantum theory corresponded to the area of a surface in the gravitational theory. In other words, the geometry of space-time emerged from the structure of entanglement. This result applied to special theoretical models, not to the universe we observe, yet it provided a powerful conceptual pathway. It suggested that space-time might not be fundamental, but a macroscopic reflection of microscopic correlations. Some researchers began exploring whether a similar principle could operate in a universe like ours. If space-time emerges from entanglement, then the cosmological constant might also reflect deeper informational properties. Perhaps the small value of the vacuum energy is not a direct sum of quantum fluctuations, but an emergent feature of the underlying structure. This perspective does not offer a complete explanation, nor does it replace the success of general relativity. Instead, it suggests that the gravitational laws we observe may arise from constraints on quantum information, much as temperature and pressure arise from molecular motion in a gas. These ideas remain firmly theoretical, lacking direct experimental confirmation. Yet they provide a framework in which the otherwise baffling cosmological constant problem becomes part of a broader question. If geometry is emergent, then vacuum energy might be emergent as well. The acceleration of the universe could be a reflection of how entanglement networks evolve, not the effect of a mysterious substance filling space. For now, these concepts serve as an intellectual compass rather than a final answer. They guide the search for a deeper understanding of gravity and quantum fields, suggesting that the solution to cosmic acceleration may lie in the unseen architecture of space-time itself. But the universe also offers direct clues through observation, and some of those clues appear in the form of small, persistent anomalies. The next chapter turns to these subtle inconsistencies, examining what they reveal about the limits of our current model. For all the elegance of the Lambda, cold, dark matter model, the universe continues to whisper hints of complexity that do not fit neatly within its equations. These hints do not overturn the model, nor do they undermine the vast body of evidence supporting it. Instead, they appear as subtle tensions, persistent enough to draw attention, fragile enough to demand careful handling. They are signposts on the boundary between understanding and uncertainty, reminders that even in an age of precision cosmology, the universe retains its ability to challenge human expectations. One of the most significant of these tensions is the disagreement between measurements of the present-day expansion rate. Early universe observations, particularly those from the cosmic microwave background, point toward a specific value of the Hubble constant. This value is derived from patterns imprinted in the ancient light of the universe, patterns shaped when the cosmos was only a few 100,000 years old. When interpreted through the Lambda cold dark matter model, these patterns reveal the geometry, composition, and evolution of the universe, leading to a precise estimate of the expansion rate today. But late universe measurements tell a slightly different story. Using the distance ladder method, astronomers calibrate the brightness of Cepheid variables and type Ia supernovae to determine the distances to faraway galaxies. The redshift of these galaxies then reveals the present-day expansion rate. The result is consistently higher than the value inferred from the early universe. Both approaches are rigorous. Both rely on tested physics. Yet the two sets of measurements do not overlap within their uncertainties. This discrepancy, known as the Hubble tension, has persisted despite years of refinement and scrutiny. Scientists have explored numerous possibilities to explain the tension. It could arise from subtle, systematic effects in the distance ladder, perhaps in the calibration of Cepheid variables, or in the behavior of supernovae. It could emerge from assumptions built into the interpretation of the cosmic microwave background, where small changes in the early universe could influence the inferred expansion rate. Or it could signal new physics. Some models propose a brief episode of early dark energy that modifies the expansion history before recombination. Others explore whether neutrinos or other light particles possess properties not fully accounted for in standard calculations. None of these ideas is confirmed, yet each reflects an earnest attempt to understand the divergence between observation and prediction. A second tension arises in measurements of cosmic structure. Surveys of weak gravitational lensing, which examine the tiny distortions in galaxy shapes caused by intervening matter, suggest that the universe may be slightly less clumpy than predicted by the Lambda cold dark matter model. The difference is small but persistent across independent surveys. This parameter, often expressed through a combination of matter density and clustering amplitude, appears lower than expected from the cosmic microwave background. This S8 tension, while not as statistically striking as the Hubble tension, contributes to a growing sense that the universe may be hinting at dynamics not fully captured by the standard model. Scientists approach these tensions with caution. Weak lensing measurements require extraordinary precision. The shapes of galaxies must be corrected for atmospheric effects, instrumental distortions, and intrinsic variations. The connection between galaxies and dark matter must be modeled with care. It is entirely possible that subtle systematic effects influence the results. Yet the persistence of the tension across multiple surveys encourages continued study. If the difference reflects genuine cosmological behavior, it might point toward a new understanding of the growth of structure. Other anomalies contribute to this landscape of questions. Strongly lensed quasars provide independent estimates of the expansion rate, often aligning more closely with the late universe values. Measurements of galaxy clusters sometimes suggest slight deviations from expected growth patterns. The distribution of galaxies in cosmic voids occasionally hints at small mismatches between observation and simulation. None of these differences is large enough to claim new physics, but together they form a constellation of clues that guide scientists toward deeper investigation. These anomalies do not weaken the success of the Lambda cold dark matter model. Instead, they highlight its precision. The fact that such small differences are even detectable speaks to the extraordinary accuracy of modern cosmology. At the same time, these tensions serve as invitations, encouraging researchers to refine their models, improve their data, and explore new theoretical directions. As the universe reveals itself in greater detail, these anomalies remind us that scientific progress is driven not only by what aligns with expectation, but also by what diverges from it. They open doors toward new interpretations and new possibilities. Whether they represent hidden systematics waiting to be uncovered, or the first signs of new physics, remains unknown. The next chapter turns toward the future, exploring how the coming decade of observation may bring these mysteries into sharper focus and reveal whether cosmic acceleration is a window into deeper laws of nature. The mystery of cosmic acceleration has carried scientists from the quiet flicker of distant supernovae to the deepest questions about spacetime and quantum fields. For more than 2 decades, the universe has revealed a steady truth. Its expansion is not slowing but speeding up, driven by a force or property that remains unknown. The Lambda cold dark matter model has guided the interpretation of this discovery with clarity and success, yet it leaves profound questions unanswered. As the 21st century moves forward, a new era of cosmology is beginning, one that may bring the answers that generations of researchers have sought. This era will be shaped by an extraordinary collection of instruments and observatories. Each new mission will examine the cosmos with a level of detail that earlier generations could scarcely imagine. Space telescopes will trace the shapes of galaxies with exquisite precision. Ground-based surveys will capture the night sky again and again, building a dynamic map of billions of objects. Gravitational wave detectors will listen to the universe's deepest vibrations, turning the mergers of black holes and neutron stars into cosmic rulers. Together, these tools will measure the expansion history and the growth of structure with unprecedented accuracy. The European Space Agency's Euclid mission will chart the positions and shapes of billions of galaxies across a vast portion of the sky. By measuring weak gravitational lensing and baryon acoustic oscillations together, Euclid will provide a powerful test of both cosmic geometry and structure formation. It will reveal whether the universe truly follows the predictions of general relativity, or whether subtle deviations begin to emerge when distances and structures are measured with greater precision. The Nancy Grace Roman Space Telescope will approach the same questions from an infrared vantage above Earth's atmosphere. Its stable and precise imaging will strengthen the measurement of supernova distances and clarify the relationship between cosmic acceleration and the present-day expansion rate. Combined with the Vera Rubin Observatory's immense time domain survey, Roman will help refine the distance ladder with unparalleled detail, reducing the uncertainties that contribute to the Hubble tension. Meanwhile, gravitational waves will open a new pathway into cosmology. Standard sirens, created by the mergers of compact objects, offer a direct measurement of distance through the amplitude of their waveforms. When paired with redshift information, these events yield independent estimates of the expansion rate. As detectors grow more sensitive and networks expand, These measurements will become a powerful complement to traditional methods, offering a way to determine whether the Hubble tension reflects new physics or simply the limits of previous techniques. The cosmic microwave background, too, will continue to play a central role. Future ground-based experiments will refine measurements of its temperature, polarization, and lensing patterns. These observations will sharpen constraints on early universe physics and further limit the possible explanations for deviations from the standard model. If new particles or fields influence the early expansion, their signatures may appear subtly within the cosmic microwave background's fine structure. Yet observation alone will not answer the puzzle. Theoretical physics must advance alongside the data. Researchers will continue to explore whether dark energy is a constant property of spacetime or a field that evolves over time. They will test whether modifications to gravity can explain the acceleration without contradicting solar system experiments or gravitational wave measurements. Others will pursue the idea that spacetime emerges from quantum information, seeking a theory that unites geometry and entanglement in a single framework. These avenues are uncertain, but they reflect the willingness of science to explore possibilities wherever evidence guides. The next decade holds the promise of clarity. If the Lambda cold dark matter model remains correct, the coming wave of observations will confirm its predictions with remarkable precision. The value of the equation of state parameter will tighten around -1, and the growth of structure will align with the expectations of general relativity. The anomalies that linger today may fade as measurements improve, revealing the model's simplicity as a true reflection of the universe. But if new physics waits beyond the horizon, the universe will reveal it. A measured deviation in the equation of state, a persistent difference in the growth of structure, or a gravitational wave observation that defies expectation could open the door to a new chapter in cosmology. Such discoveries would reshape our understanding of energy, space, and time, offering insights into the unity of the quantum world and the cosmic fabric. No matter which path the future reveals, the pursuit itself carries a profound significance. The search for the cause of cosmic acceleration is not only a quest to understand distant galaxies or ancient light. It is a search for the deepest laws that govern reality. It challenges human imagination, pushes the boundaries of knowledge, and asks questions that touch the foundations of physics. Why does space expand the way it does? Why is the energy of the vacuum so small? What principle sets the curvature of the universe? As the final words of this narrative settle, the mystery remains. The universe continues to accelerate, quietly and steadily, carrying galaxies farther apart with each passing moment. Scientists stand on the threshold of discovery, armed with instruments of extraordinary precision and guided by questions that have shaped decades of inquiry. The next chapter belongs to the cosmos. It will reveal the truth in its own time, through the faint light of distant stars and the invisible ripples that travel across space-time. The search continues. The answers await. The universe expands.